it's linked up. I did it in my period 4 class. So I'm really trying to do that for every lecture we're doing here. And I think I have. I think I've done that. Okay, so here's kind of our big note page. Okay, can you guys at home see that? Can you see
yes,
it?
we can. Yeah, we can see it.
Okay, great. Okay, so here we go, jokes. We need jokes today. Okay. And this is actually, these notes right here are notes that are not, I kind of changed these yesterday. And I just kind of changed it, try and explain it a little bit better. But I'm going to leave that up, give you guys a minute or two to write this down. Okay, here we go. I got a couple. A single guy decides life would be much more fun if he had a pet. I hear during the virus, pet ownership has went way up. So he went on to the pet store and he told the owner that he wanted to buy an unusual pet. Well, after some discussion, he finally bought a centipede, a 100-legged bug, a centipede, 100-legged bug, which came in a little white box to use for his house. So he took the box back home, found a good location for the box, and decided he would start off by taking his new pet to church with him. So he asked the centipede, he looked in the box and he said, "Would you like to go to church with me today? We will have a good time." But there was no answer from his new pet. That bothered him a bit, but he waited a few minutes and then he asked him again, "How about going to church with me and receive blessings?" But again, there was no answer from his new friend and pet. So he waited a few minutes more, thinking about the situation. He decided to ask him one more time, this time putting his face up against the centipede's house and shouting, "Hey in there, would you like to go to church with me and learn about the Lord?" A little voice came out of the box and said, "I heard you the first time. I'm putting on my shoes." I know, that was pretty good. Okay, here's a couple one-liners. What was the coach looking in space for? An all-star team. An all-star team. And the last one, what part of the body is like a musical instrument? Your nose. You pick it and you blow it. There you go. That's something. What is life going to be like without AP chemistry? Oh, don't answer that. It'll be so much better, right? Okay, I want to write these equations on the board here. So talk about this. So this is going to be now the third way that we can write out the differential rate law, or really the rate law. We have the differential rate law with ratios. We have the integrated rate law with graphs, and now we're going to use reaction mechanisms. So I've got NO. So we're going to write the overall reaction and the rate law. So here is, for example, 2.
Mr. Wood, would you be able to move the computer down a little bit?
Thank you, Kara. Thanks for telling me that. Is that better?
Yes, thank you.
Thanks for telling me. So do this. We're gonna have to be told the slow step and the fast step. So let me finish this, and I'm gonna do these. This is the kind of thing, definitely fair game. I was noticing it yesterday, working with some students on the lab questions, the quiz questions. Definitely our test and definitely the AP test as well. Okay, so if you read the top of this, reaction mechanisms. So most reaction mechanisms involve more than one elementary step. So the two I've got here have 2 steps. On the next slide is going to be one with 4 steps. So usually 2, 3 steps, 4 steps. They produce intermediates, which I'm going to talk about today. I want to talk about intermediates versus a catalyst, and that again is something that is going to be on our test. They involve a sequence of steps called elementary steps, and that's what I have here. I have these two reactions, 2 separate reactions that both have 2 elementary steps. One of these elementary steps will be slower than the rest. It's called the rate determining step. So I think I don't know if I mentioned this to you guys or my period 4 class yesterday. But to me, like something that's the slow step determines how fast a process takes. Like a great example for me, I live on the west side of Highlands Ranch, kind of over by the football stadium, kind of over by Shea Stadium. My kids went to Thunder Ridge back when they were in school, so 10 years ago they went to Thunder Ridge. But when I go up into the city for something, then I go up Santa Fe. And every time the rate determining step is right around Arapahoe Community College. And you guys, if you think about it, if you've driven up Santa Fe, there's like a series of 3 steps there. And I know that if I can get through there really fast, that's right by Arapahoe Community College, I'll be able to get to my destination faster. But if there's a lot of traffic, those lights will back everything up. Point I'm making is there's in any process, the slow step determines how long the whole rate will take. And so that's the key here, is the slow step is the rate determining step. The differential rate law, number 4, the differential rate law, that again is rate is equal to K times A to the first, B to the 0, or whatever. It's what we were working on a little over a week ago. The differential rate law, number 4, indicates all species up to and including the slow step, okay? Talking about the reactants. The rate law reflects on the reactants up to the slow step. The exponent for the reactants is the number of reactant molecules up to the slow step. Okay, we need to do some examples. Okay, so they rarely involve more than 2 molecule collisions. So like I was talking about yesterday, unimolecular, bimolecular, termolecular, very, very rare. Okay, so we're going to do 2 things. We're going to write the overall reaction, and we're going to write the rate law for this mechanism. So what I'm going to do here is if something is common on the left and the right, I'm going to cancel that out. So what that is N2O2, let me say that right, N2O2 gas on the right in the step 1, on the left in step 2. So I'm going to cancel that out. Okay, and that is the only thing that, again, is on the left and the right. So the overall reaction here then is what's left over. So I've got NO gas, and I really have 2 of them. So I have two NO gases plus Br2 makes 2 NO-Br gas. So that is the overall reaction. And again, we've done this process before in terms of looking at something common on the left and the right. We did this when we were doing half reactions with redox reactions. We did this when we were doing delta H in the law of summation. So we did this a couple times. But what we haven't done here is the rate law. So what I do for the rate law now, so this is the rate law. So I got rate, here's the rate constant. I look at the slow step, and I look at everything that's a reactant, And the exponent here in the rate law reflects how many of those there are, that up to, including the slow step, that have not been canceled out. I'll say it again. So I look at the reactants, and the exponent here is going to be how many of those there are that have not been canceled out, up to including the slow step. So in this case, I have NO, and I have two of them, 1 plus 1, 2. So that is here. So this is one place, and I made a huge point way back a couple weeks ago when I said something we're going to talk about when we get into chapter 13, when we write out equilibrium constant expressions, is that the exponents are the coefficients. And I said we don't do that in kinetics. But here we do. So this is when we have a reaction mechanism. The exponent is going to be how many of these reactants that have not been canceled out. So since there's one BR2, it would be like this. So here is the overall reaction. So this is where we canceled out things that were common. And then here is the rate law. And again, the whole thing that's key about the rate law are the exponents. And so this time, the exponents reflect how many there are that have not been canceled out, up to including the slow step. Okay, I'm going to go on to the next one, and then I'll take your guys' questions. And we're going to look at a few more of these here in the next few slides. Okay, so if you look at this, what are things that are common on the right and the left that can be canceled out? Like I see NO3 here, and I see NO3 here, so I can cancel that out. Can anybody here in class or at home see there is something else that's common on the left and the right that can be canceled out?
NO2.
NO2, very good. So NO2. And I don't think there's anything else. So my overall reaction then, on the left, I have NO2 gas plus CO gas. And then over here, I've got NO gas plus CO2 gas. Okay, so there's the overall reaction. And again, hopefully that's not too bad because we kind of have done that before, stuff like that. Okay, now the rate law. So what I said is the rate law reflects the reactants, and the exponent is how many of those there are that have not been canceled out, up to including the slow step. So here is going to have rate is equal to K, and the slow step is the first step. So all I have is NO2. Now, the NO2 canceled out because of this, but before the slow step. So what the rate law, it reflects up to including the slow step, but not after the slow step. So the NO2 was canceled out. This NO2 was canceled out after the slow step. So that means before the slow step, that had not canceled out. So there was two of them. So then NO2 squared. So for the overall reaction, I canceled this NO2 out. But for the rate law, because when I got to the slow step, I hadn't canceled it out yet. And again, the exponent reflects how many NO2s there were, up to including the slow step. Okay, I want to look at a couple more of those. Before I go ahead, questions? Okay, so here's the next slide.
Mr. Wood, would we not include CO? Would we not include CO2?
We do not include CO2 because CO2, Mason, is that you, Mason, asking that? It's a product.
But would we include CO?
And we wouldn't do CO because it's after the slow step. It appears after the slow step.
Okay.
So the slow step is the dividing line. So you go up to including the slow step, but nothing after the slow step. And again, kind of the logic in explaining that is my example of, again, if I'm driving up to the city, if I can get past the all the lights there by Arapahoe Community College, I can go pretty fast. And that's why, but what determines everything is the slow step. Okay, so I include all the reactants. The exponents on those reactants reflect the reactants that have not been canceled out, the number of the reactants that have not been canceled out up to including the slow step. Okay, let's look at this reaction here. Okay, I'm going to leave that up for just a second, then I'm going to erase it. So we're going to write the rate law now for this reaction. So this reaction has 4 steps. So again, I'll say it again to try and say this right. So the rate law reflects all the reactants up to including the slow step, and the exponent is how many of those reactants that have not been canceled out up to including the slow step. Okay, so on this reaction, and I don't want to go too fast here, but if you look at this, the I is produced in the first step, but it's canceled in the second step. The slow step is the third step, so I is not going to be included. The same thing happens with X, because it was produced in the second step, but it was canceled in the third step. So again, if we've gotten to the slow step and it's been, whatever has been canceled out, I'm not going to include it. So all I have here is A and B. And the Z is, to Mason's question, good question, but Z is a reactant after the slow step. That's why the slow step determines everything here. And so Z is not present because it's a reactant after the slow step. Okay, so the trick here now is what are the exponents on the A and the B? And those reflect the number of these that are present up to including the slow step. So for A, in step 1, in the first step there's an A, in the second step there's an A as a reactant. So it would be second order in terms of A. Somebody tell me, what would be the exponent on B? It would be 2 as well, right? Because they haven't been canceled out.
Would you be able to move the camera up a little bit?
Thanks, Kara. Again, is that better?
Yes, thank you.
Good. So this would be the rate law for that reaction mechanism. Ethan.
Wait, so it's all the uncancelables, right?
It's all the uncancelable.
So in the example 2, isn't it only one NO2?
But see, this was canceled out after the slow
Oh, I
step.
see. Okay.
Good question. And this is one of those things, I think with a little practice, it's not too bad. Okay, I'm going to move ahead. Hopefully I'm not going too fast. Speak up if I am. Am I going okay, Alex? Doing okay? Okay, let me put up this one. I'm going to let you guys look at this one. So it says, for the following reaction, so we're given this reaction, CH3Br plus I iodine, so on. The following mechanisms were proposed. Which mechanism is most plausible? 1, 2, or 3? The key thing here, the key clue is at the bottom. They give us the rate law. They say the rate is equal to K CH3Br to the first. Okay, go ahead and take a second and look at that. See if you can figure out which mechanism is the most plausible here. So again, we're given the rate law, and the rate law is equal to K to CH3BR1. So they're telling us that. That means at the slow step, the only reactant that there is CH3BR, and there's only one of them. And Tyler here just said, hey, is it 2? And he's exactly right. The answer there would be 2, because in mechanism 2, the only reactant I got, again, is CH3BR, and there's one of them. And if you look at the first one, it's not a mechanism, it's just the overall reaction. So the first one, the rate law would be CH3BR to the first. It would be rate is equal to K times CH3BR to the first and I negative to the first. So that's not a possibility. And in the third one, the slow step is the second step. So really you'd have CH3BR to the first, CH3 positive to the first, and I negative to the, I'm sorry, you'd cancel out the CH3BR. So you'd have, in the third one, the rate law would be CH3BR to the first and I negative to the first. The answer to this question is number 2. Okay, I'm going to move ahead unless I'm going too fast. Okay, so now we're going to go and we're going to connect reaction mechanisms. So we've got reaction mechanisms connected to the rate law. Now we're going to connect them to activation energy diagrams. And if you remember what we did yesterday, and I showed you the video, I thought it was kind of a cool video, with the nitrogen triiodide and just how reactive it is. But remember I said that the smaller the activation energy is, the faster the reaction is going to go. And I said the bigger the activation energy, the slower the reaction is going to go. So here, relating EA, remember capital E, lowercase a means activation energy diagrams to mechanisms. So a couple little things here. Okay, so first of all, if there's 2 steps, notice there's 2 peaks. So the number of peaks in the activation energy diagram tells you how many steps there are. So there's 2 steps and there's 2 peaks. The bigger peak means the bigger activation energy means the slower step. So the bigger peak represents the bigger activation energy, so the slower step. So the number of peaks represents the number of steps. The bigger peak represents the slow step. And the final thing, remember endo and exothermic, and this one even says endothermic, and remember endothermic means the ending is above the beginning. The ending is above the beginning, which occurs here. Okay, so you can tell from the activation energy diagram, 2 peaks, 2 steps. You can tell the second peak is bigger, so the second peak means the second step is the slow step. And then you can tell it is endothermic because the ending is above the beginning. Okay, so then question is then, what would this diagram appear, or how would this diagram appear if the first elementary step was the slow step? Okay, so think about it for a second. So how would the diagram appear if the first elementary step was the slow step? So if the first elementary step was the slow step, and there's still 2 steps, it would be like this, and then like this, and then how would the ending, where would the ending be relative to the beginning? Still endothermic, so it would be higher. So we have step 1, we have step 2. This would have to be the slow step because it's a bigger activation energy. And because the ending is above the beginning, this would have to be endothermic. So here we're connecting the reaction mechanisms. We connected them to rate laws, the differential rate law. Now we're taking reaction mechanisms and connecting them to activation energy diagrams. Okay, so here's an activation energy diagram and a couple steps. I'll let you guys look at this. Again, hopefully this isn't too difficult. But if you've looked on the lab and if you've looked on the quiz, there's questions like this, and there'll be questions like this on the test. So I'll give you a second for those that are taking notes and want to sketch this down and answer these questions. How many steps in the mechanism? Which step is the slow step, endo or exothermic? So how many steps in the mechanism? There's 2 peaks, so there has to be 2 steps. Which step is the slow step? Step 1 or step 2? Which step's the slow step? Step 1, right? Because it's, Alex is exactly right. Step 1, because it's the bigger activation energy. So the answer to number 1, how many steps in the mechanism? 2, because there's 2 peaks. Number 2, which step is the slow step? The answer would be step 1, because it's got a bigger activation energy. And then finally, this would be exothermic, because the products are below the reactants. Okay, almost done with chapter 12, monster chapter. Okay, I want to skip this page. But I do want to do this page. It's going to be the last thing we're going to go over, a catalyst. And there's some stuff here that I haven't included that I'm going to write on the board. The difference between a catalyst and an intermediate. I'm going to write, there's 2 things, and you need to distinguish between these. I'm just going to write these on the board. A catalyst versus an intermediate. We're talking about a catalyst here. And these are different. So the difference between these, I'm just going to slow down here, let you copy these down, and I want to do an example of both of these. So a catalyst is something that makes the reaction go faster. It's actually in the overall reaction, and I'll show you on the next slide what I'm talking about. It's not reflected because it cancels out. But it jumps in, it makes everything go faster, and it does that by lowering the activation energy. And that's what the two graphs at the bottom show. The catalyst lowers the activation energy, makes the reaction go faster, but at the end, it comes back out as a product. And that's why a catalyst, the way you recognize it in a mechanism, you're going to see this on the next slide, but it shows up first as a reactant right in the very first step. But it comes out as a product in the last step. So in the overall reaction, you cancel it out. It's not included, but it makes the reaction go faster. The kind of another thing connected to this, but it's different definition, is an intermediate. Instead of being first seen as a reactant, but then canceling out as a product, this is first seen as a product, so it's on the right side in one of the beginning steps. Again, depends on how many steps. Usually the first step, but a beginning step, but you cancel it out as a reactant. So it's kind of the opposite. A catalyst first appears as a reactant and then comes out as a product, where an intermediate is first seen as a product, but then it's canceled out as a reactant. But a catalyst lowers the activation energy, makes the reaction go faster. So if you remember way back, we said that the rate constant depended upon two things. It depended on temperature and a catalyst. Okay, and so this shows us, so they work by one of two methods. They change the mechanism so that not as much kinetic energy is required for the reaction, therefore a greater percent of molecules can react. Okay, so the graph showing there's just not as much energy required to get the reaction to occur. Okay, here's the reaction for showing ozone. Ozone is O3. And so O3, so the overall reaction is ozone plus ozone to make O2. And here is, there's reaction 1 on the top, or mechanism 1 on the top, and here's mechanism 2. And so the point of this question here is to identify anyways, back, I'm going to let you guys copy this down. Again, almost done here, so I'm going to stop here in just a minute. But in this reaction, in the second one, so where it says versus, so we have reaction 1, we have mechanism 1 on the top, which is O3 plus O3 makes 3O2, so one-step mechanism. Versus, so where it says versus, so these are two steps. Okay, and the point of this question is to ask you, what's the catalyst? And what is the intermediate? What's the catalyst and what's the intermediate here? So in the second mechanism, versus, so we have two steps, O3 plus Cl, arrow OCl plus O2, and then step 2 is O3 plus OCl, arrow O2 plus O2 plus Cl. Okay, so a catalyst shows up as a reactant in the first step, but you cancel it out as a product in the second step. So in that second sequence, what's the catalyst? Chlorine. Chlorine is, right? Good. Chlorine. Because it's a reactant in the first step, but you cancel it out in the last step. An intermediate, on the other hand, is first seen as a product. So it shows up in the first step as a product, but then you cancel it out as a reactant. What's the intermediate? OCl, thank you. OCl. And so recognize the difference between a catalyst and an intermediate. So, okay, that I'll show you real quick the rest of this chapter, and I could talk about more stuff like I was going to talk about. I'll just talk about this real fast. I want to give those guys in class, if you have any questions or you want to look at the quiz, we can do that. But This is a reaction O2 plus ultraviolet light makes 2O, and then O plus O2 makes O3, which is ozone. Okay, and so what this is this is how ozone is made. And ozone is important in the upper atmosphere because ozone absorbs ultraviolet radiation, and which is dangerous for us because if we're exposed to too much ultraviolet radiation, we're going to get skin cancer. But they noticed years ago, they noticed that there was a hole in the ozone layer in the northern hemisphere in the winter. Well, if you look at this, why in the winter, because this is showing the production of ozone, why in the northern hemisphere in the winter would there not be as much ozone? UV is light from the sun. What's the story about the northern hemisphere in the winter and the sun? There's not as much sunlight, right? We got a bunch of snow on the ground right now. Well, there wasn't as much ozone being produced. But at the reaction that I got on the board, there was a big time going back that they thought chlorine was a catalyst for the breakdown of ozone. So again, going back 20, 30 years, there was even more than that, 30, 40 years. They thought that chlorine was a catalyst, and so these things called chlorofluorocarbons were really limited, and they were banned because of the thought there. But they noticed, and so they thought, okay, well, the northern hemisphere, there's a hole in the ozone. Well, that's because there's not as much ultraviolet radiation. What do you think the story was in the southern hemisphere in the summer? Of course, their winter, our summer, there was an ozone hole in the southern hemisphere because it was winter in the southern hemisphere. So, okay, let me just, I'm just going to, because none of this stuff is stuff I'm going to have on the test and the quiz. There was one thing here about how catalytic converter worked, and again, the use of a catalyst. So, okay, I'm going to stop there. We are done with chapter 12. We got to where I wanted to get, which is good. Those in class, this time's for you. Again, I have the key to the quiz out. I'll come around if you have any questions you want to go over. At home, if you want to just hang in there, you can. I'll come around to you guys in a second. If not, you guys are dismissed, and I will see you guys tomorrow. We're going to start chapter 13.
Thank you, Mr. Wood.
See you guys.
Thank you.
See you guys. See you, Kara.
Thank you.
Thank you.
See you guys.